Okay, great. So, hi everyone. For those who don't know me, I'm Cher. I did my PhD at Imperial, and currently I'm working with Emma Robinson at King's College for my postdoc. So today I'll be presenting ongoing work on interpretable classification using a variation autoencoder with visual attribution mapping. So we developed a method for classification with visualization between classes. And this is motivated by the need of medical image analysis to use more explainable models with better feature visualizations. In particular, the method is based on generative models, so a variation autoencoder with a GAN to help with capturing all salient features in a class, and in addition, a classification module on the VAE latent space. So to validate our methods, we applied it to various data sets, including the Human Connectome project with simulated lesions, ADNI, which is an Alzheimer's data set, and Biobank for age or sex prediction. So coming back to interpretability, it's now a very big branch of deep learning and is broken down mainly into intrinsic methods and post hoc methods. Intrinsic method might innately try to explain decision of the model, for example, decision trees, or other methods will have certain modules that focus on particular features of an image. For example, capsules can encode class-specific features in the same capsule and thus have interpretable features. However, post hoc methods that are most usually applied after a model is trained and can be often applied to any model. So of particular interest in this talk is feature attribution methods. So these methods visualize features or parts of the image important for a particular class. However, because these methods depend on the power of the network it's applied to, the network might focus on the single most important feature in the image rather than all relevant salient features. And that will appear in the visualization. So ICAM lies between intrinsic and feature attribution. It's an intrinsic model using a VAE, which learns to generate feature attribution maps to capture differences between classes. So the use of a VAE encourages the network to learn more about the data and therefore have more salient features. So going forward to explain ICAM. So ICAM is a translation network with classification. So it translates between different classes that encode an input in two latent spaces. So we have the attribute latent space encoding class relevant information and the content latent space encoding non-class relevant information. In addition, there's a classification module on the attribute latent space, which allows the space to be separable, but you can still interpolate between and within classes since it's a shared space. We use the translated images to generate a visual attribution map or a difference map between two specific inputs. So ICAM builds on a method called DRIT, which is also a translation method with attribute and content spaces, but I won't have time to go into the differences since it's a very short talk. So our goal is to visualize differences between two classes. So here is a simple example of MRI brain slices. So one image on the left here is class 1 with simulated lesions or blobs. Class 0 has no simulated lesions, and what we're interested is the innate differences in the class. So in this case, we're only interested in visualizing the blobs rather than the actual differences in the brain shape and the cortex. So coming back to ICAM, here we have an overview of how we achieve translation and difference map between two specific inputs. So taking in input X of class 0 without lesions and input Y of class 1 with lesions. The inputs are encoded using a shared attribute encoder to encode class relevant features. So both of these inputs are passed through the network to create an attribute latent space, ZA. At the same time, these inputs are passed through a different network which is a content encoder, again shared between all different classes to encode non-class relevant information. These are then swapped so that we can achieve translation, and the swap content and attribute spaces are passed to the generator, thus generating an output which is of the same content but of different class. So in this case, you have output mu, which takes in class 0 but the content y, and thus we can create an attribute map, which is the difference between mu and y, which is the same content input, and therefore we can generate these specific differences between the inputs. In addition, we have two other modules, a discriminator to improve translations and generations, and another very important part of the network, which is the content discriminator, which introduces adversarial loss in order to have class invariant content space. This allows the disentanglement between the attribute and content space, so that attribute only encodes class information and content will encode non-class relevant information, in this case, the shape of the brain. So moving forward to some preliminary results. So at the beginning, we're using simulations on an MRI data set. So these are two slices with constraint lesions. So class 0 has no lesions. Class 1 has a lesion mask. Again, no lesions. Class 1 has lesions in 8 different locations, and this is indicated by our lesion mask here. So going forward, some qualitative results. So here we have the results of ICAM when we interpolate between class 0 and class 1. Input A of class 0 and its mask, input B of class 1 with lesions and its lesion mask. So here what we see is the generations of the brains with the corresponding attribution map, which encodes the differences. So what we want to see here is a smooth interpolation of adding and removing the lesions. So because this is a cyclic method, we can go both forward and backward. We can interpolate from an input with lesions to an input without lesions. So this is the interpolation in the attribute latent space. So here we can see that ICAM can both add lesions, which is shown by white here, as well as removing lesions, which is shown in black. Now comparing to DRIT, which is another method doing translation, here we show that DRIT can indeed also remove lesions quite well, but it doesn't add the lesions as well as ICAM. It only learns to add lesions in very specific locations, and it cannot learn the different spatial locations of different lesions. In addition, we don't observe smooth interpolation, and we think that's due to the fact that the content space hasn't been fully disentangled, which is mostly related to the architecture of DRIT in comparison to ICAM. ICAM can also interpolate within class, since we have a shared attribute latent spaces between all classes. So in here we have example of input A from class 1 and input B. So each input has different lesions. So it shows the power of ICAM that can not only remove lesions, but also remove and add lesions as appropriate. So for example, looking at this example, we can see that the lesion on the left here is being added, whereas other lesions are being removed at the same time. Again, in comparison to DRIT, DRIT is not able to do very good interpolation within classes. Is only really able to remove lesions and is unable to add lesions as appropriate. To further illustrate this, we've done a comparison comparing different components of the different networks. NZ is the attribute latent space dimension. So in the original network, they use a latent space of size 8. we also tested with the same latent space size as ICAM for comparable comparison. And different components of ICAM, for example, with a classification module with the difference map loss and an L2 loss. So what we compare is the normalized cross-correlation between the masked lesion and the visual attribution map. So obviously adding lesions is far more difficult. So we see that the score here is lower than for removing lesions. And we see that with each component that we add to the network, an increase in score. And finally, ICAM performs the best across all the different scores. Of course, DRIT does not have a classification module and therefore does not have an accuracy score. So coming soon, we have experiments on HPC with 3D MRI and lesion simulations. The ADNI dataset, which compares Alzheimer's patient to MCI patients, and biobank with age and sex. So just as a little preview, this is an example image that we trained biobank on ages of young and old people, and we can see that the ventricles are being detected, which is a very well-known phenomena in aging, where you have an increase in the ventricles. Yeah, finally, thanks for listening. And yeah, I'd like to thank my people from my group, Metrics, and especially Emma Robinson. And yeah, thank you very much.